Thank you, Mark. Thanks everyone for having me here today. Thanks for accommodating the schedule so I can present in the morning Europe time. I'm currently based in Saarbrücken, which is in between Frankfurt and Paris. So it's a shame I can't be in Adelaide. Mark just mentioned that I've been in Adelaide for several months, but not until now. So I can only be virtually with you today. But I think this is better than nothing. So I'm very happy I can be virtually with you here. So I'm leading a research group on human-computer interaction at the University of Saarland, which is in Saarbrücken, home to a number of research institutes. So this is one of the biggest sites for computer science research in Europe. Maybe some of you have already been there. If not, make sure to pass by next time you're in Central Europe. I'd be very happy to host a visit and show you our work. This group here. So this is my fantastic team. This was, I think, at a big demo that we did at Kai a few years ago. And the work that I'm going to present today is, of course, mostly their work. So all credits go to my students and postdocs who have been working and are working with me. So today, obviously, I want to talk about haptics, which is a major theme of our research. And I think this connects closely to what you guys have been working on, are still working on in your projects during this winter school. And as far as I'm informed, your projects are primarily about tactile prototypes, right? So about feedback that you apply directly on the skin, directly on the body to users, for instance, by vibrating or using electrotactile vibration. And I think this is the most common way of haptic feedback. Yet it is not the only one, but still a very, very important one. And that's essentially what we have focused on a lot in the past 10 years or so in my lab. And here are just some examples of some research that we've done on tactile research to get us, on tactile haptics to get us started with this talk here. So I think one of our special focus areas is very thin and body conformal and highly ergonomic haptic technologies. So for instance, we have been working on multi-touch sensors that are flexible, even stretchable, and can be wrapped and worn on the body or integrated inside textiles. We have done similar work for physiological sensing, for instance, for EMG sensing that can capture muscle activations. And we do this with temporary tattoos and very, very thin electrodes that can directly contact the body. We're using similar technologies for electrotactile output. This is actually work that has all started with Anusha, and I know that Anusha is now doing very impactful work in that space, and I think some of you are working with his toolkit this very week. So we have used this for various things, including haptic illusions, which I think is a super exciting area where we can sort of trick the mind, human mind, to believe there is something that they can feel which is actually not there. So for instance, what we did is we used electrotactile feedback to make surfaces that are hard appear soft to people. So they can press on, say, for instance, a hard table surface, but it would still feel soft, and you can even control in software how soft this should be. And I think that's a quite exciting area for all kinds of tactile haptics that can be further explored. We worked on displays. Here's one example of a very thin and stretchable display that we fabricated in the lab. And we also worked on vibrotactile output and vibrotactile design. But today I don't want to talk about tactile haptics because I know that you're already spending a lot of time on tactile haptics this week. I want to introduce an orthogonal, a different area of haptics, and this is body actuation. So I think one observation we can make is that the field has worked long on tactile feedback and is slowly moving into a new area, which is about actuating the body. It's also oftentimes called kinesthetic feedback. So this is all about creating movement on the body, as opposed or in addition to creating something that you can feel with mechanoreceptors on the skin's surface. This is also often subsumed under this term of proprioceptive haptics. So feedback that our proprioceptive sense is processing, it's feedback on body movement and on body position. And I think this nice conceptual image that Hilary Brooks from AIML in Adelaide actually has produced when I gave a talk over there shows quite nicely this vision of augmenting the body to behave in different ways, to be able to move in different ways, possibly to slip into new roles, virtual roles or realistic roles, based on how our body can feel and move and behave differently. And I think that's a very exciting space. And today, I hope I can get you excited about this area of body actuation too. So why do I believe this is fascinating? Because there's a number of things we can do with body activation that we can't necessarily do with conventional tactile haptics. So for instance, we can enhance people, we can support them with strength and additional forces for manual tasks that they perform. This is the realm, for instance, of supernumerary limbs, additional limbs, as you can see here, that give workers extra arms that can help them perform difficult physical activities. Or we can support dexterous activities like this work here that I like a lot. DigiSync from the WIS community has been showing where additional arms can help people just do things more carefully or with more precision and more dexterity. Another big benefit of body actuation is, of course, that we can support body strength and physical activities, for instance, to enhance the mobility of people or their endurance in physical activities. Here's one example of a commercial exoskeleton, low body exoskeleton from Hypershell, which is not very expensive actually and can support people quite well in giving them extra strength or also resisting their movement when they're on the go. And I think that's an exciting area, not only for the elderly in an aging society, but also for supporting people in everyday activities, in sports, in exercise, and in other areas. Last but not least, we can use these technologies as well for enhancing human perception and enhancing human bodily expression. And I will show one example from our research here later that shows how we can change embodiment and allow people to have a body that feels different than their original one, which presents novel opportunities in VR, but also for areas such as simulation, for instance. So that's the overall area, and what I want to show today in a brief sort of whirlwind tour through some of our research is three main aspects. The first one is looking at how we can create body actuation that is personalized and ergonomic. And I think this is super important to enable the HCI community and designers and domain experts in using these technologies, which so far have been largely restricted to specialized robotics labs. Second, we will talk about how we can make these technologies such that they really integrate with the body, with humans' perceptions of their body. And I will show one example of embodiment in XR, where we make people feel differently depending on what avatar they are representing and controlling. And then last, I want to talk briefly about AI. I mean, obviously AI is the big thing, and I think it's also getting a really big thing for haptics. And I will show how we can use modern AI technologies for designing haptic feedback that is human-like and natural, and really captures the nuanced behavior that as human beings exhibit when we move or when we interact in the physical world. And I will also show how we can use such technologies for creating designs that are scalable to large environments. But let's first look into the personalized and ergonomic body actuation. And here I would like to present some work on two main classes of body actuating systems. So one class of system is the exoskeleton space. Here we actuate the existing body. So we help people move their body, move their limbs, their existing limbs in a different way. The second example is more about how we can augment and enhance the body in ways that is not our natural body shape. Quite some work has been done in robotics about what is called supernumerary limbs. I mentioned this briefly before. This is adding additional body parts, most often arms or extra fingers, but it could also be artificial tails or even ears have been shown. So quite interesting ways of how we can enhance the body itself. And I think we also need new ways of making these happen. As I mentioned briefly before, so far these technologies have been mostly restricted to specialized robotics labs or to very expensive hardware that can't be tinkered with. So one of the main goals of our research here in my lab is to lower the barrier of entry and really make it easier and easily possible for a wide audience of people to use these technologies so they can explore opportunities, they can design them, they can test them. So here we're focusing more on low fidelity implementation or medium fidelity implementation rather than upper end production strength technologies. This is really to give people some technologies at hand so they can start becoming creative and testing out things. So here we think, of course, people like us in HCI, who so far have been largely prevented using these technologies, but we're also thinking of interaction designers, for instance, or domain experts like in rehabilitation or in the medical space who could explore novel avenues for these technologies. And I think the underlying assumption is that I believe there is many more application areas that these technologies can support than what has been explored so far in robotics. And I think HCI is the community to explore these. But again, we need to empower the HCI folks to get these things done. I want to show two work here that we've done in the past 2 years. And the first one is ExoKit. This supports exoskeletons. So here the idea is that we provide a prototyping toolkit, which actually is open source and open hardware, free for everyone to download and to use. The key idea is to support people quickly creating their own exoskeletons in various configurations. It comes with 3D printed modules where we share the 3D design, so you can easily print those modules on your 3D printer and then flexibly and easily assemble them in many configurations. For instance, here you see a configuration that supports both arms. Here's just one arm. Here's just the elbow. So we have different modules actually that can be flexibly combined, and you can make this more complex or less complex depending on what your application is requiring. The most complex scenario so far is 6 active degrees of freedom. That means we can control movement in 6 directions on both arms. The actuation is done with Dynamixel off-the-shelf strong servo motors that you can buy off the shelf and add. Also, there is different motors available that you can choose from. So you could use a weaker one if you don't need strong actuation forces, or a stronger one, depending on what you need. It's also possible to equip some of these degrees of freedom with sensing-only capabilities. So you can sense the position, but not necessarily actuate. So we really designed this with the key idea in mind to make this as flexible as possible and lightweight to implement. And so here's one example where you see Marie, who was our lead author, my PhD student, who has been driving this research, varying one configuration of the exoskeleton. That's the first version. We have just iterated on it and have a version 1.1, which we demoed at Haptics last week, which is slightly more integrated and has a smaller back and a sort of better support on the backside. We will also be sharing this shortly. So if you're interested in exoskeletons, this could be a good technology for you to get started. And as said, you can just easily replicate it. Maybe I should say one word about exoskeleton actuation versus electrical muscle stimulation, because our community is also heavily invested in electrical muscle stimulation, as many of you may know. That's a technology where you apply electrodes to the body that directly actuate your own muscles yourself. And the benefit of EMS is it's very lightweight because you don't need to wear an exoskeleton. But the problem with EMS is that it doesn't give you real force support, right? It's actuating your own muscles, so it doesn't give you extra strength. And maybe more important even for our application is that the benefit of exoskeletons with servo motors is that we can precisely adjust the force that is provided for assisting the user, or also for providing resistance if this is necessary. And that would not be possible with EMS. Also, we can precisely control what degrees of freedom will be actuated, where assistance is provided, versus those that are free for the user to move freely and naturally, something that is not possible in the same way with EMS. So I think these technologies occupy complementary spaces, and depending on your application, you can choose which one you want to go for. A challenge with robotic technology is not only the hardware, but also how do we control it? And programming this real-time feedback loop where the user is moving and we want to augment or resist user movement in real time can be quite demanding. And to ease this entry barrier for the software side as well, ExoKit also offers a software side, a software toolkit with quite powerful abstractions. So in addition to the low-level functionality, sensing only or moving those actuators, which is the standard, right? In addition, we abstract to higher levels. And this goes all the way up to, for instance, guiding users' motion, constraining them to certain movement, or guiding them towards specific targets, and doing all of this in essentially just one function call. And then our internal software framework keeps tracking users' movement and makes sure we apply in real time these guiding forces towards a certain target or away from a certain target. So this is all nicely encapsulating. You don't have to bother about this if you want to implement it. And so one example is the next one. I just want to show quickly that various kinds of things and novel applications can be realized with such a toolkit. Here we look at a collaborative body play game. So what we have here is one user on the left, Alex controlling the user on the right. And so it is his arm movement that is controlling Marie's arm movement. But to make things a bit more interesting, we have not made a direct one-to-one mapping, but we flipped things around. So directions and also the mapping between joints have been changed. And so their goal is together to figure out how their bodies are virtually linked and then solve this physical piece where they need to put these strings on the appropriate handles over here. And so then this can look like this one here. You see they have to really figure out and carefully try to get this done. And I think my argument here is that all of this mapping between these two exoskeletons was implemented with one key function call that defines this mapping. And then all of the continuous interaction is dealt with by the software framework. So that's ExoKit. I briefly want to mention another line of research that looks at supernumerary limbs, so additional robotic arms. And here the key challenge is that these need to integrate with the body, of course, similarly to exoskeletons, but they may even have a more varied way of how we realize them and how they are being worn. Because these could, for instance, be worn, as we see here, on the shoulder or on the upper arm or on the forearm. And depending on the user's size and the reachability constraints where this additional arm should be able to move, this hardware may need to be realized in quite different ways. And so what we propose here is a computational design approach where we essentially use computational modeling and digital fabrication to make highly personalized robotic arms possible. And I will just very quickly walk you through the key idea. The key idea is that we start recording the user's body, including the body size and proportions, and the range and the type of motion that the user wants to perform with this robotic arm. So the next we define what is the desired area where the end effector should be able to reach. And then optimization kicks in and optimizes the entire hardware for us. So here we see how the user is demonstrating movement. We're capturing this with a markerless motion capture approach using an RGB camera. And this gives us the detailed skeleton of the user, including the range of motion of these activities that the user wants to perform. Then next, in a graphical interface, the user can, or the designer can select where the robotic arm should be mounted. You see this here. And the next one can also specify what is the volume or the target area where the interaction should happen. I think we see this probably on the next slide. Yes. So this is here. So for instance, we can say the end effector should be able to touch the body, make interactions on the body, and then we can define what is this area on the body. And so then once this is defined, automatically the dimensions of, or initial dimensions of the end effector are adjusted. And then we use a global optimization approach using simulated annealing where we simultaneously optimize for several conflicting goals. So we want to maximize reachability, but also minimize stress on the skin where the robot is mounted. We want to minimize collisions with the body under the movement that is happening, and optimize several other ergonomics criteria that would be really hard to optimize for if you did all of this manually. And so then this creates an initial configuration that people can inspect for different poses. As you can see here, by clicking on them, you would be seeing how this robot behaves under different key poses. And then we can further tweak parameters if we wanted to and iterate on the design. And then the final outcome is a specification that essentially defines the length of these individual links that we see here. And then in this specific case, we created them with aluminum rods, but this could also be 3D printed in an alternative approach. So the key argument here is that body-based technologies need to be personalized, oftentimes in terms of their dimensions and mounting locations. And while we, of course, can do this manually in many cases, it may be beneficial to use computational approaches to optimize them more. And so then, for instance, this can help us having a third hand, like we see here, when we need one in tinkering and construction tasks. We could use it as a third hand when we need assistance on the go, like this example here. Now the robot helps with holding this large package here. Or a third example that I like quite a bit, this is for haptic feedback for those who have fear of spiders, for training in behavioral therapy. So then this actually creates haptic feedback, tactile feedback on the human body using this brush-like end effector that you see here. So these were just two approaches that show how we can help people more quickly and rapidly build their own wearable actuating devices for haptics. A last point I want to make quickly is that I think an important next step is moving on beyond the rigid technologies that we have seen to soft robotics. So we so far used rigid technologies because these can exert a lot of force, which is helpful oftentimes, but at the same time, this can be more bulky and more heavyweight. And I think an important next step is to really think about how we can use soft robotics technologies that of course do exist in the robotics space and integrate them with prototyping toolkits for the HCI and design community. Here is some work that we've done in this space before, particularly on textile robotics, For instance, the work that you see in the middle is a textile material that can automatically actuate using embedded shape memory alloys, which is a smart material. But one could also use pneumatic technologies like these ones here, for instance, to enhance how we exert forces on the human body. So we haven't done anything concrete in that space yet for toolkits, but I think that's definitely an important next step. And if you're interested in it, let me know. Maybe we can even collaborate. So my second key argument I want to make today is that these technologies that actuate the body should be deeply integrated, not only in terms of their ergonomics, their physical design, but also in terms of their behavioral design or perceptual design. So people should really perceive them as being part of their own body or as modifying their own body. And so in order to investigate this space, we looked into one specific instantiation, which I think is a great test case, which is avatar embodiment in virtual reality. So those of you who play games in virtual reality know that there is many different avatars, self-avatars that you can control in virtual realities. And of course, these have very different behaviors. So for instance, you could have a sort of a very technical robot that you're controlling, maybe a cute small teddy bear, maybe a huge giant tree folk. And it goes without saying that if you embody these, if you control these, your behavior should be different. So far, the feedback that users get when they're controlling these avatars is mostly visual, right? So you can, as you move your body or provide input with a gaming controller, you can see how your avatar is moving, and most likely these different classes of avatars will be moving quite differently. So you can see it, but so far you cannot feel it. It is not your body that feels different depending on whether you slip into the role of a teddy bear or of a tree folk. And this is what we wanted to address. And here we've been inspired by some prior work that started working on this, for instance, work from Japan that added some actuators on the elbow joint to mimic a bit the experience of a robotic joint. Or this work here, Pump VR, that simulates the weight of an avatar using some haptic technologies. And so we want to further explore this space. And the key idea here is that we had using kinesthetic feedback, meaning using body actuation. And we want to use this to align the physical movement capabilities that users really have when they're in VR. We want to align this with the expected style of how an avatar would move. So for instance, if you control a teddy bear, probably your movement should feel very different than if you're controlling a giant tree folk. And what we do here in VR is we track users' movement to control the avatar. This is classical VR. But then in addition, we add this feedback loop, this haptic feedback loop that allows the user to feel through body feedback how the avatar moves. So we can enhance movement or resist movement to make this more alike the avatar is likely to move. Technically, we enable this work motion styler based on the exoskeleton that I've just shown you. Here we see my PhD student David wearing it on the forearm, and we provide feedback in this entire area of the upper lip. One example is shown here. Here we use this for controlling a now we have a problem because both videos don't seem to be aligned. Let me see whether I can get this working. I'm sorry, this doesn't work the way it should. So what we should be able to see here is Marie controlling this virtual dragon here. And what we're doing here is as she's flying this dragon, she's getting feedback through the exoskeleton that makes her arms really feel like she's controlling it, flying these large wings, which contributes to this feeling of embodying an avatar or a dragon that she's embodying here. Likewise, when we're controlling a robot, maybe the robot's motion should be fast and constant and precise, quite technically. And so we can provide feedback that makes this happen. Here we see how David's natural movement is supported in this way. Speed and acceleration is increased here, and targeting is made more precise. In contrast, when the user is controlling a large tree folk, we can assume this is slow. Motion should be really slow. They should be heavy. Maybe they should be imprecise. And we are dynamically modulating David's body movement to make that happen. And the key question that we investigated in this WISP paper, beyond these individual examples, is investigating systematically what are motion properties that are relevant for embodying humanoid avatars in VR, in addition to a few examples cases that we've seen here. And this brought us to a conceptual space that I will just walk you through very quickly, which looks at multiple aspects of motion that can be modulated. One of them is the weight of motion. We can make motions more heavyweight or more lightweight. So for instance, here we are providing assistive force to make natural motion feel more lightweight. And of course, we can add resistive forces that work against the human body to make the same motions feel more heavyweight. Likewise, we can adjust the speed or the acceleration of movement. We can also change the range of motion, adding constraints. So for instance, we can restrict users' range of motion to certain angles, restricting them in the way they can move. So for instance, a small teddy bear might not have this large range of motion, so we can really constrain this to smaller angles. We can add and control the targeting style. For instance, make targeting more precise by guiding users and effectors toward certain targets. Or we can make it more imprecise by making it actually really difficult for people to precisely hit a target, creating some overshooting or undershooting as we go. And there's more aspects that we investigate in the WIS paper, which I won't mention here today. But I think the key idea really is there is a big space of how we can influence how people perceive their own motion capabilities. And there's a principled way of how this can be done. We've implemented this in a design tool where we have presets that people can select for different avatars, and then they can additionally and optionally fine-tune properties of motion behavior if they want it. And then after the avatar has been generated, the entire system works in a loop automatically. And as soon as the user is moving, the system would automatically apply the corresponding types of feedback. Now, what does this do with the user? The interesting thing is that we have seen in an evaluation that providing such kinesthetic body feedback really helps people adopt the motion of an avatar. So what we see here is a control condition on the left. This is a visual-only case where participants could see the avatar. And on the right, we have in addition provided kinesthetic proprioceptive feedback for the robot, teddy, and treefolk avatars. And what we see here is that in all those cases, people rated the way of how they adopted the motion more positively. And I think one quote that I like quite a lot is the one on the right that I will read out loud now. So one participant said, I learned I have to move very slowly because of the feedback. And so now I have to think differently. That was actually with the treefolk avatar. Now I have to think like a tree, for example. I have to plan my movements more because I cannot easily redo them. So this technology really brought the participant into thinking they have to think more like a tree, plan their movements differently because they know this is going to be slow. And so I think this is one strong signal that shows that people have really integrated these specific motion capabilities of their avatars, thanks to the feedback technique. On the other hand, what we also have seen is that these types of feedback slightly decrease agency. So why is this the case? It's actually to be expected, because as soon as you are not yourself anymore, but you are a treefolk, then this may sort of somehow decrease your feeling of the agency that you have. For instance, you can't move as fast anymore as you wanted, right? So we have seen some slight decrease in agency here, but still, and I think that's the important finding here, participants still felt strongly in control. We're still in the positive range of agency all here. So then I think this the exact goal that we're having with these types of system is to adjust the agency that you have for specific agentic behavior. So this brings me to the third part of my talk, where I want to talk about how we can use AI for supporting haptic design. And here I will talk about two different problems. One of them is, how can we make sure body actuating systems behave in a very nuanced way, in a very human-like way? I guess what we want to certainly avoid is a system that behaves like a classical conventional robot, right? It makes your body move like a robot in typical cases. Maybe that's okay if you want to control a robot avatar, but in others, it's certainly not. So how can we make sure this behaves as flexibly and naturally, if you want, as people do? And the second problem is, how can we scale up to rich environments without having to manually design everything? But let's talk about the first one here. Here we looked at how we can learn from human nuance, detailed movement for designing haptic feedback technologies. And we did this in the example of robotic arms that are worn on the body and help people do activities. And in these activities, it is of course important to hand over objects. For instance, here we see that a screwdriver is handed over between the robotic arm and the user. We wanted to make sure that the movements of this robotic arm and the handover is as natural as possible, particularly because these technologies are mounted on the human body. This is, of course, a very sensitive space. We want to make sure that this is not harming the user, but also not even intimidating or scaring the user because it might move very fast or in areas too close to the body. So here we really want to make sure this behaves as human-like as possible. And of course, it should also work during ongoing primary activities and with this asymmetric roles where there's, of course, one main user and then the assistive robotic arm. It would be very difficult or even impossible, I think, to apply traditional heuristic methods for robotic control here. So instead, we used a data-driven method to capture this nuanced human behavior. And the way we did this is we captured a lot of human interactions in a motion capture studio. And here you see how the setup was like. We had one participant, the lady standing here, who is the user, the human user. And then we asked the second participant to sort of behave as if they were an assisting robotic arm. So you can see that they were seated in a configuration that is similar to a hip-mounted robotic arm. And then our hypothesis was that human users would, of course, respect aspects of perceived safety, of what is appropriate speeds and distances, etc., but also what is an appropriate timing of when our object should be handed over or taken away from the human user. Here we have not included any speech commands or conversation. Instead, we have fully focused on body pose only. So the key goal is to really learn from this nuanced body motions that we're seeing here. And we've used this for creating a quite big data set. We call this 3 hands, a data set for natural handovers between humans and supernumerary robotic limbs. We have captured data from 12 participant pairs in 12 daily activities, including rich skeleton data and hand poses, and also a manual annotation of when handovers are happening. And so this data set can then actually be used for training models that automatically control robotic arms following this nuanced behavior that we're seeing here. And as an example, we have trained or generated several models. One of them is a model for generating the trajectory of the handover, so the movement, the trajectory of movement of how the robotic arm should move. Here we have used a conditional variational autoencoder, which is essentially an encoder-decoder architecture that we train on this data that we have seen here. And then we use it in real time to decode the next pose of the robotic arm. And here you see some examples. In red, we see ground truth. In green, we see the model. And what this shows here is that this generative architecture creates plausible and quite natural and quite diverse types of motions based on the user data that we're seeing here. So this is not a classification task, I should say, but it is a generation task. So we do not want to generate exactly what we have seen, but something which comes realistically close while offering some variety. Another model generates the region of transfer, so where should an object be handed over? And the third one predicts when an object should be handed over or taken away from the user. And I think this is also quite an interesting result because we have seen that on this nuanced data from human users, we can actually train a model that quite accurately predicts when is the right time of handing over objects. That means the user does not have to communicate, now I want to have this object, but they would simply behave naturally, maybe slightly slowing down the activity or briefly looking at the robotic arm. So they can use their implicit behavior that people have demonstrated. And so from these subtle cues, the system does identify what is the appropriate time frame of handovers. And this, of course, can make the interaction between a human and a robotic arm more smooth and more natural, because the robotic arm simply behaves like a human companion who would not necessarily need to be asked to hand over an object, but who would just identify now actually is the right time for handing over this object. So this is 3 hands, was a Kai paper last year for generating body-based feedback. The second piece of work I want to show here briefly to end with is looking at some other case. Here we look actually at vibrotactile haptics, and this is actually about skin-based haptics, so not body actuation, but classical vibrotactile, so very compatible with what you guys are working on currently in the winter school. I decided to add this to just show one other aspect of how AI technologies can be used for haptics. So in the previous example, as you know, we have captured quite a lot of data and then trained our own generative models. In this example here, on the contrary, we just leverage plain visual language models. So we leverage the semantic world knowledge that is encoded in VLMs without capturing more training data. And so the approach or the key goal that we are tackling here is how we can design haptics at scale. An example that we looked at is a virtual reality world, similar to the one that you see here. Of course, it generalizes to other worlds as well. The key idea being that there may be many objects in this world. These objects may have different vibratory behavior. For instance, the fridge might vibrate in a certain way. The pen on the stove top might vibrate if it is boiling water. The microwave might vibrate, and so forth and so forth. Now, in classical design, haptic design, for each of these objects, the designer would need to manually design a haptic response. And even then, it would be difficult to compose all of them in a realistic scene. Here we were wondering about, is there a different approach where we can sort of do this automatically or almost automatically, just based on information that we have in the virtual reality world? And the answer is yes, this is possible to a certain extent at least, thanks to modern VLM models. So what we do here is we provide a new architecture in which we automatically design biprojectile feedback to each object in a VR scene. And we really do this automatically without designer intervention. And the way we do this is we infer what are semantic attributes of these objects and what is their physical context. So the input is simply the VR scene as you would have it in a typical VR development environment. And an observation here is that this scene does contain multimodal information. It contains information about geometries, but also some more information about objects. It may have information about how they are composed, and might have some labels or additional information given by the developer about what these objects are. So we then apply a set of chained LLM components to automatically infer some haptic-based properties using a VLM just based on this automatically gathered multimodal information from the VRC. And then we use this information to render in real time haptic feedback based on some physical properties of how vibrations propagate across adjacent objects. I won't go into all details here. If you're interested, you can have a look at the paper. It's all detailed in the paper, but I just want to give you the key and the high-level idea here. So the high-level idea really is that we start with the VR scene, and this has a number of information that we can parse. For instance, we can, and we do actually render images of the scene, but also of individual objects from different perspectives. First of all, we analyze what is the scene category. What type of scene are we seeing here? Is this a kitchen? Is it a playground or whatsoever, a bathroom, etc.? We can use the scene name that is provided by the developer, but what we've seen empirically is that oftentimes developers don't spend a lot of time in carefully naming these properties. So oftentimes they just keep dummy labels, things they have downloaded or whatever. So oftentimes this is wrong. So that implies that we use a VLM here to check the scene name against what these scene images suggest the scene is about, and then this finalizes what scene category we're working with here. And then next, each object is analyzed in sequence based on these images that we have about isolated objects, but also about how these objects are positioned within their larger context. And then we use this to analyze haptic-related aspects, such as what material is it made of, what's this object type, what's the size of the object, and does it vibrate, etc. So to give you an example, this is a rendering of the scene we have, and then scene category would be assigned kitchen. Then for individual objects, for instance, for the dining table here, the VLM would assign dining table as object category, material category wood, and it says most likely this dining table doesn't vibrate. In contrast, a smartphone is made of plastic and might likely vibrate. And then for the objects that are in the scene, we use the VLM to identify material properties in more detail. That's important to inform how vibrations propagate across adjacent objects. And we also analyze the objects that may vibrate in more detail, trying to understand what is the type of vibration that we're seeing here and what might be keywords associated with it. So the key idea really is that we use the semantic knowledge of the VLM to identify properties, haptic-related properties of all of these objects automatically at design time. And then during real time, during use time, we can use this to render haptics, render vibration dynamically based on this automatically inferred information. And we do this essentially by either using a text-to-audio model or by looking up based on keywords in an audio database. This gives us audio waveforms, and these can be then adjusted to be rendered as vibrotactile feedback. But what is important, we need to adjust this feedback depending on what are the objects. So first of all, we look at what are objects in our contact graph, where is the user currently touching the scene, and then we in real time measure, what we calculate actually, we simulate the propagation of and attenuation of vibrotactile signals across these materials. That means even if the user was not touching the original object, but close to it, for instance, touching the countertop here instead of the microwave oven, they would still feel an attenuated version of this vibrotactile response. So this is another part of scaling. We really want to not only scale up to all of the objects that are in the scene, but we want to scale to each individual touch location in the scene and make sure we have a plausible rendering for those. So then we use this information to modulate the waveform and can finally render the vibrotactile feedback. Now, unfortunately, I can't make you feel how this feels like in the scene, but maybe I can make you hear it. So we need to see whether there is audio shared in the Zoom call. I will just play back the video, and I hope that you can hear the audio signature, which is then corresponding to the vibrotactile rendering. So this attenuates, as you can see here. Objects can be moved in real time. So this is all dynamically calculated. And now you see how we can even interpolate between multiple objects based on the object contact graph and the propagation that we have in these objects. And I think this is, of course, not perfect because it is based on stochastic VLMs. But we have done some detailed evaluation. You can find the paper that makes us very confident that this can work for most objects quite well. So this could be I think, a promising starting point for more automatically generating haptics at scale in more complex environments. So this brings me to the end of my talk. I hope I really could get you as excited as I am about haptic interfaces that move toward the human body. But at the same time, I hope I could convince you that there remain hard problems to be solved that we can join forces in addressing together as a community. So we need to continue working on a physical integration. We've seen that there is first work, including toolkits that help people create more ergonomic, wearable actuating devices. But I think we need to move further to make sure we really respect the unique properties of the human body in terms of particularly the materiality, the soft materiality of the human body. And here soft robotics is a very exciting future area. Secondly, we need to integrate not only physically, but also experientially. And strongly convinced that if successfully designed, body actuation can be naturally experienced as part of one's own body. We've seen first examples in the embodiment VR example that I've shown before. But of course, it's just one example. There's more cases where we can deeply integrate the behavior of body actuation with human experience. And then lastly, AI is super important. Data-driven methods are super important to go beyond manual and heuristic designs and unleash the power of really coming close to human, realistic, nuanced, and diverse behavior that we can learn from humans or even infer from foundation models or combine both together to create more rich and more expressive and more natural haptic feedback. So that's me. Thank you so much for listening. And I guess we have a bit of time for questions, should you have some. Thank you very much.
Yeah, thank you so much, Jurgen. That's great. Thank you so much. We had one question online, actually. Let me just pop that up again. They said, Russian asked a question, how does the arm know when to support, get support from the exoskeleton, I guess?
Yeah,
Yeah.
I was thinking to further
Yeah, I think it would be helpful, Russian, if you could just tell me what piece of work you're relating to here. But I think we have an echo problem. So maybe Mark needs to...
It's okay. He'll come here.
Yeah. Oh, he'll come over here, right? Yeah.
So the question is about the arm on one of this works, and it was helping the user to grab the pens. I think you show clips of that. And so I was wondering, how does an arm know when to support the user?
Yeah. So relating to the wearable robotic arm that is mounted as a third arm on the body, right? And coming in to help with holding the screwdriver or so. And so indeed, knowing when to support is super difficult. And I think a conventional way would have been to just let the user say it or press a button, right? Says now the robot should come in, or now the robot should come back and take some objects. And I think that the one of the strong reasons why I believe like that learning from humans is super helpful is that probably by looking at human behavior, we can actually learn that behavior just from the implicit cues that we have. I didn't have a lot of time to detail on that specific model, but I briefly mentioned that we have this third model that learns the timing of hand in and hand out just from the human behavior. So when looking into this, we realized that most often this is really just based on the fact that the user keeps doing some activity and then would slow down at some point. And that's a strong cue for the model that now may be the right time for handing in the object, right? Or the user may briefly glance in the direction of the robotic arm, really just subtly and very, very briefly during the interaction. But then this may be enough of a cue for the model to infer that now is the time to hand in or take out the object. So I hope that was addressing your question. I didn't misunderstand you, Russian.
And there's another question online saying, my question is about sensory feedback for an extra virtual limb or sensation. To what extent could repeated training allow rich vibrotactile patterns delivered on an existing body area, varying in frequency, location, be perceived as meaningful sensory feedback belonging to an extra limb or sensation?
So thank you. This is a really great question that I haven't addressed in my talk today. You spotted this. So indeed, once we have this additional limb, be it virtual or be it physical, but something that is not part of our own body, a key question really is, can we not only make it behave like supporting the user, but can we allow the human user to directly feel what it is doing, right? So similar to what we did with the example that you see in the rightmost image, right? Where we allowed the user to feel the avatar. But can we make the user feel the end effector, say, of this wearable robotic arm as well? And I think that's an interesting and active area of research where groups are working on and where we also have made some contribution. It is very demanding because for each morphology or shape, one needs to think about what is a good mapping from that type of behavior to existing human sensory receptors, right, or sensory channels. So I think one interesting contribution we could make here, thanks to primarily work that has been done by a PhD student from Masa Inami, Shuto, who was visiting us around about a year ago, he worked on an artificial tail. So in this case, it was an arm, it was an artificial tail. And the problem with an artificial tail is that people can't see it, unlike a robotic arm. So he was wondering how can we provide haptic sensory feedback that allows people to really feel like what is the configuration of this artificial tail. And he came up with a skin stretch device that was mounted on the lower back of participants. And this is stretching skin in different directions and in turn creating a proprioceptive sensations as if there was a larger tail that was moving in certain directions and hence stretching the skin. And it worked surprisingly well. It was a WISP paper published last year that showed in extensive studies that people could really integrate this virtual tail to much greater extent thanks to that feedback. But I think my point really is, I guess for each individual case, one needs to think about what is good sensory mappings to make that happen.
Fantastic. Any questions in the room here at all?
Thank you. Can I add something if you can hear me?
I can hear you.
Okay. I'm the same person I asked this question. Thank you so much. It was really interesting and I got the point out here. But I'm working on the different pattern in haptic in the smaller area, but more complex. It's as we can define it somehow semantic vibrotactile. It means that I have let's say I have 60 vibrator in a small area and I can draw a shape with a different speed. And I want to transfer this concept to let's say to that moving tail or something. I understand your example is mostly to mimic the real sensation, like a tail. But I want to ask more about the conceptual, the different kind of sensation that it's involving the virtual environment. And this complexity pattern, I wanted to know how much is explored in the research area. When we play with the speed, with the frequency, and kind of a language, a haptic language.
Yeah. So thanks for that question. I can't comment on your specific application of case, of course, because I'm not familiar with it. But I think what I can say is that indeed the tactile space is moving toward more high resolution feedback lately, but actually quite lately. I mean, most of the work up until a few years ago was really based on one single vibrotactile actuator. And now, in part, thanks to work from Anusha's lab, we're seeing that this can be scaled up to higher densities and larger number of actuators. And of course, the same is true for vibrotactile as well, although maybe it can't be scaled down as easily and as densely as electrotactile feedback. So what we're seeing in the tactile space, in summary, is really higher resolution feedback already, and first design languages are emerging for that space. I think we're not seeing the same yet at this larger scale of body-based feedback, maybe also partly because body-based feedback so far is not necessarily used much for symbolic information. The way I understood your application case is you're conveying symbolic information like symbols or directions or patterns using vibrotactile haptics. In contrast, these larger scale body actuation is typically used really for coarser grained motor skills that people are supported with, or fine grained motor skills like piano playing, but not symbolic. And this may be one of the reasons why we're not looking into such high density patterns so far. That said, with today's motors and some of these fine-grained exoskeletons for hands, for instance, I think one could consider going more deeply into that specific space. It's certainly an exciting area of future work.